This is an explanation of mathematical worksheet number 2, where we did the activity with the cubes simulating radioactive decay. When you write your equation for your cubes, remember you're going to select a couple of points, pick 2 points that seem to fit the trend of the data well, one near the beginning of the data and one near the middle or a little farther, but don't use one of the end values. So you shouldn't use 0, 100, or 21, 1. That would be my preference anyway. If you did it, it's not wrong, but I would prefer that you use something towards the beginning and towards the middle to the end, but not very beginning or very end. So anyway, I picked the points 362 and 1112 because when I looked at the my scatter plot, they seemed to fit nicely. Remember that I said it's helpful when you are setting up your system of equations to use the one with the higher x value as the top equation. Now, why did I pick exponential equation? When you look at the scatter plot, it looks like it could be decreasing power or decreasing exponential. But this one clearly has a y-intercept at 0, 100, where that is your starting number of cubes. So exponential is the only one of the two that has a y-intercept, so that's why I chose exponential. Here is my work for doing my system of equations. Typical mistakes, if your equations didn't turn out well, typical mistakes are switching x and y. So remember, the x value goes as the exponent here, and the y value goes on the left-hand side of the equation. When you divide, remember to subtract the exponents. You don't divide the exponents. And then you use the reciprocal power or a root to find what b is. B should be somewhere in the neighborhood of 80 to 90%. If you got something, 79%, that would still be fine. If you got something really different than that, then probably something went wrong. Then substitute b back into one of the equations and calculate that number, divide 12 by that number, or divide the left-hand side of your equation by that number, find a. A should be somewhere in the neighborhood of 100, because remember, in an exponential function, the coefficient is the y-intercept, and our y-intercept for our data is 100. So you might have something lower than 100, something higher than 100, but it should be a number that's fairly close to 100, maybe somewhere between 80 and 120. Now I know that's a pretty big range, but with data it's hard to be exact sometimes. Okay, now problem number 8 was pretty challenging, so let's take a look at problem number 8. Problem number 8 was asking you to look at kind of the theory behind radioactive decay and then compare that to your equation and what you got. So because our cubes have 6 sides and one side was marked, we would expect on average about 1/6 of them to decay or be taken away each trial. And that's about 16.7%, which means the percent that would remain is about 83.3%. Notice that number should be pretty close to the base of the function that you got. So here's my function down here. The base of my function was about 81%, pretty close to 83%. So you should notice that. Now, how do you figure out what the half-life is? So based on this probability, estimate about how many trials it would take for the half of the cubes to decay. Now I show some work here doing it by hand, but I want to also show you on the calculator. If you start with 100 cubes, we'll just push enter. Oh, I need to downsize this a little bit so it's easier to see. So let me make this, so there we go. And then we multiply that by 0.83, then push enter. That's be about what we would expect for the first trial, the number of cubes left. Then after the second trial, maybe around 70. Third trial around 58. Fourth trial around 48, and so on. So you can see here, to get half of the cubes to disappear probably takes around 4 trials. So if we look, and so now let's check doing an equation, solving an equation. So to get the half-life, how long would it take for half of the cubes to decay? So using my equation, how long does it take to get down to 50? So setting the equation equal to 50, I divide by the coefficient, then calculate that number. Now I have an exponential equation, so I use logs to solve it. And remember, using change of base formula, you could have log of 0.4356 divided by log of 0.814. So these are two different methods of doing it. And I ended up with 4.037 trials. So my answer is very close to my estimated half-life. Now, here's a big idea, is recognizing the key parameters of an exponential function. When x is 0, we have the base raised to the 0 power, which is 1. So the coefficient here is the starting value when x is 0. So this represents the starting number of cubes. The base is the rate of change. If I started with my original number and kept multiplying by 0.814, then I would get a smaller number of cubes with each trial. And so, as I said before, notice that your base should be close to about 83%. Okay, let's take a look at the very last page now. Okay, in the tire problem, the punctured tire problem, I chose an exponential function rather than a decreasing power function because it makes sense to have a y-intercept. At time 0, there is air pressure in the tire before it's punctured. So we would expect to have a specific value for the air pressure. Once again, I went through this process, so you would want to go ahead and look at the work here. I picked those 2 points, but kind of compare that to your work. I ended up with B is about 94.62. So basically, this is a percent of the air pressure that remains in the tire after each second, and this would be the initial air pressure at time 0. Okay, and then, oops, that's not what I wanted. Go back to my last page. And then this last problem, which was the water flow, water pressure problem. This one has a curve that looks like this, which is one of the shapes of a power function. It makes sense that a power function that is increasing, either concave up or concave down, is going to go through the point 0, 0. And it makes sense that when water pressure is 0, the flow rate out of the hose would be 0. So we are going to use a power function for this data. So instead of having y equals ab to the x, like with the exponential function, we have y equals ax to the b. So the base is your x value, and the other side is your y value. Once again, I put the larger x value on top, so when I divide, I get, rather than a fractional value, I get a number greater than 1. Once again, not absolutely necessary, but I just prefer doing that. So I divided the y values. Remember, and then you can divide the bases, because 50 to the b over 5 to the b is the same as 50 over 5 to the b. So I got 3.2 is 10 to the b power. And then I used log base 10 of 3.2 is b. Since that was a base 10, that was really handy to do. Found out what b was. B, remember, is the exponent. Now remember, in your power functions, when you have a base, or when you have an exponent that is between 0 and 1 but is positive, that gives a shape of the graph that's similar to a square root function. And notice 0.5 is actually really close. 0.50514 is close to 1/2, so this is almost exactly like a square root function, because x to the 1/2 would be the square root of x. Then I substitute, then I finish solving for a, and I get 0.887. And when I put this through the points on my calculator, it fit very nicely. And remember, on the front page I gave some instructions for how to go to on your graph menu, analyze plot function, then it opens up a little box. You can type in the equation and see how well it fits your scatter plot. So hopefully that explains some of the things about the worksheet. If you have any questions, further questions, please come and ask me.